The industrial world of the past and of the present was and still is instrumental in providing us with many of the comforts of modern life. The combined products of plants like this one make up the world that we live in today. If we looked inside many of these plants, we would see how different many of them are in their operations and in the products they produce. But in many ways, they're also similar. Inside a plant, in any plant, there are many different kinds of processes. Some processes seem fairly simple, such as maintaining a preset level of water in a tank. Other processes are much more complex, such as a process in which chemicals are mixed with water in specific proportions. Some processes are relatively small in size and in operation, compared to other processes which can be quite large. But regardless of the size, complexity, or purpose of a process, most processes in today's plants need to be controlled in some manner to assure efficient and safe plant operation. Process control can be achieved in many ways. This program will touch on some of them. Process control can be achieved in many ways. Now, some of these you should already be familiar with, such as the different types of control modes, like proportional, reset, and rate. But there's another way of achieving control that, combined with the different control modes, works to make control more effective. This other way of achieving control has to do with how the control instruments are arranged. And as instrument technicians, you need to know about some of the basic control arrangements if you're to be able to adjust and maintain the control systems in your plant. As you may recall, the four elements of a control loop are the primary or sensing element, the measuring element, the controlling element, and the final control element. These four elements will be present in every process control loop. Now, in some loops, the primary and measuring elements may be combined in one instrument casing, or the measuring and controlling elements may be combined, but the four basic elements are present. Now, the way that these four elements are arranged and how they're utilized can vary according to the requirements of the process to be controlled. For example, you may recognize this as a feedback control loop. Feedback control senses a change in a process variable and sends a signal through the control loop to correct the error and return the process variable to set point. On the other hand, you may recognize this as a feed-forward control loop. Feed-forward control senses disturbances and provides a correcting signal through the control loop, usually before the disturbance can cause an error in the process variable. Both the feedback loop arrangement and the feed-forward loop arrangement are useful process control loops. Essentially, one senses a change in the process variable and corrects errors after they occur, and the other anticipates changes in the process variable and attempts to prevent errors from occurring. We'll look at these two control loops and several other loop arrangements later in this program. But first, let's look at a simple air compressing process and see how it can be controlled. Many plants have air pressure systems that supply compressed air throughout the plant for uses such as air tools for drilling or grinding, or pneumatic control instruments such as this pneumatic control valve. So many operations rely on compressed air that without a controlled supply, many plants couldn't operate. The compressor is driven by a motor that operates at a constant speed. The compressor takes air from the atmosphere, compresses it in its cylinders, and forces it into these receiving tanks, or receivers. When air is required in the plant, it is drawn from the receivers. In order to make sure that there is enough compressed air to satisfy the requirement of the equipment in the plant, the pressure in these receivers must be kept within a certain range. This system has been adjusted for a pressure range of approximately 85 to 100 pounds per square inch. In addition to being directed to plant equipment, compressed air is also directed through a pressure line to an instrument like this one, which we'll refer to as the controller. Although we call this a controller, this instrument performs the functions of the sensing, measuring, and controlling elements in this control loop. It senses the pressure, measures the amount of the pressure, and compares it to one of two pressure values. One of these values is a high value, in this case 100 psi. The other value is a low value, in this case 85 psi. When this instrument receives a pressure signal below 85 psi or above 100 psi, it acts like an on-off controller. For example, if the pressure drops below 85 psi, the instrument opens a valve, allowing the air pressure signal to continue to the final control element. The air pressure signal from the controller closes a valve in the compressor called an unloader valve, allowing it to force air into the receiver. The final control element in this system is the valve in the compressor. When the pressure in the receiving tank increases to the upper range of 100 psi, a signal is transmitted to the controller producing an output signal. That opens the unloader valve in the compressor, allowing air to escape rather than being compressed into the receiver. The reason we showed you this air compressing system is so that you could see an example of a process with a simple control loop. What we're going to do now is look at an illustration of this process and control loop to introduce some new terms and concepts that we'll be using throughout the rest of this program. In this illustration, the compressor and motor are represented by this portion of the graphic. The compressed air from the compressor is fed through this line and into the receiver. In this air pressure system, the process variable is the air pressure in the receiving tank. Because air pressure in the tank is the variable we want to control, it's also called the controlled variable. In addition, in this system, we're monitoring how much air pressure is in the tank, and the system variable that's monitored is referred to as the monitored variable, or, as it's often called, the measured variable. Here, the measured and controlled variables are the same. In other systems, they can be two different variables, as we'll see later. Coming from the tank, we have a line which supplies compressed air on demand to various processes in the plant. The pressure gauge, which indicates the amount of pressure in the tank, and the pressure sensing line, which directs compressed air to the controller. The controller combines the actions of the sensing, measuring, and controlling elements in this control loop. The final control element is an unloader valve in the compressor. By opening and closing the unloader valve, we can manipulate the flow of compressed air to the receiving tank. The system variable that is manipulated is sometimes referred to as the manipulated variable. Controlled variable, monitored variable, and manipulated variable. We'll be using these terms consistently throughout the remainder of this program on basic control loops. Two concepts that we should discuss here are single element control loops and multiple or multi-element control loops. A single element control loop is a control loop that usually contains only one primary element and provides only one input signal to the controller. For example, the control loop for this diagram has only one primary element, so this is a single element control loop. If this loop had two or more primary elements, providing more than one signal to the controller, it would be a multi-element control loop. In the succeeding portions of this program, we'll be looking at several different arrangements of single-element and multi-element control loops. We'll also look at some plant examples for each loop and why the particular control loop is the right one for the process it controls. Before continuing, review the material in your text. If you have any questions, be sure to ask your instructor. Behind me is a boiler furnace. It's a common process in many plants. The lower portion is the furnace, where a mixture of fuel and air is burned. The heat that it creates is used to change water to steam. The cylinder at the top of the furnace is a boiler drum. It holds the water that's heated by the furnace. Now, this process actually involves several control loops working together to control air, fuel, and water. For our purposes, we're going to look at just one part of this system to see how a single element feedback control loop can work. The control loop we're going to look at can be used to control drum level in small, low-pressure boilers having relatively stable flow characteristics, or as one portion of a more elaborate control system that would be required to control drum level in a large boiler. But before we do that, let's briefly review the concepts of feedback control and single element control. With feedback control, when the controlled variable changes away from set point, an error signal is generated, causing the controlling element to produce a signal that adjusts a manipulated variable and returns the controlled variable to set point. The feedback feature becomes evident after the error has been detected, and the control loop acts to correct the error. If the controlled variable continues to move away from set point, or if it begins to return to set point, the primary element also senses these changes. Then the measuring element produces a signal that is proportional to this change, feeding back this signal to the controlling element. The controlling element will compare this feedback signal with set point and adjust the final control element to correct the error based on the new signal. With single element control, the control loop has only one primary element, providing only one input signal to the controlling element. Single element feedback control is one of the most common control loops used in today's industrial plants. You'll probably spend more time working on these than any other type of control loop. Now, the controlled variable that we're interested in the boiler furnace process is the level of water in the boiler drum. Let's take a closer look at the boiler drum and some of the instruments that make up its control loop. The first thing we're going to look at is how water level is monitored in this drum. As you can see, a section of piping is installed near the end of the boiler drum. One end is connected to the upper portion of the drum, and the other end is connected to the lower portion of the drum. Extending from this pipe are two tubes. One tube comes out of the lower end of the pipe, and a canister type of object called a reservoir is attached to the upper end of the pipe. The other tube extends from this reservoir. Both tubes are connected to a level transmitter. Now, in this case, the primary and measuring elements of the control loop are combined in this level transmitter. We'll describe what it does a little later. A signal from the transmitter goes to this controller. The controller performs its four functions of measuring, comparing, computing, and correcting. The controller sends a signal to this control valve, which opens or closes to increase or decrease the flow of water to the drum. Now, out here in the plant, it's difficult to show you how the control loop for this process looks altogether, because the instruments are spread out. The transmitter's at one location, the control valve's at another location, and the controller is way back in the control room. But we can show you how this system looks using a simplified illustration. In this illustration, this is the boiler drum. As you can see, the drum is partly filled with water. The upper portion of the drum contains steam. The controlled variable is water level. On this side, water is fed into the boiler drum. This is the manipulated variable, because the amount of water flowing to the boiler is manipulated by this valve. Over on the other side of the boiler is the section of pipe, and connected to it, two tubes that run down to the level transmitter. The lower tube is connected to the lower end of the pipe and is filled with water that comes directly from the boiler drum. The other tube is connected to this reservoir. Steam from the upper portion of the boiler condenses inside the reservoir and fills the tube with water. Both tubes are connected to the transmitter. In this control loop, the transmitter functions as both the primary and measuring elements. The primary element, then, is a sensing mechanism in the transmitter which senses the pressure exerted by the columns of water in both tubes. The pressure exerted by the column of water in this tube is used as a reference pressure because it is fairly constant. The tube is filled and exerts a constant pressure. The pressure exerted by the column of water in this tube is variable. The amount of pressure varies as the level of water in the boiler drum changes. The primary element in the transmitter senses the difference in pressure between the two columns of water. This difference in pressure is called differential pressure. This differential pressure is an indication of the actual water level in the boiler drum. The measuring element portion of this transmitter measures the differential pressure and converts it to a signal representing drum level that is transmitted to the controller, where it is compared to set point. The controller calculates any error and sends an appropriate control signal to the control valve. The control valve opens or closes to increase or decrease the flow of water to the boiler drum. As the drum level comes back to the desired level, the signal generated by the level transmitter is fed back to the controller. When the feedback signal is equal to set point, the controller produces a signal that will hold the control valve in its new position. Now, this completes the single element feedback control loop. It's called single element because this loop contains only one primary element, which is combined with the measuring element in this transmitter, and provides only one input signal to the controller. It is called feedback because the control loop works by correcting errors in the controlled variable after they occur. Now, we said that single element feedback control is one of the most common control loops used in today's industrial plants. But it isn't the only type of control loop. Different processes require different types of control. We'll look at another type of control loop that you should be somewhat familiar with, called single element feed-forward control, when we continue. First, review the material in your text. Be sure to ask your instructor if you have any questions. As we said earlier, there are many different processes in today's industrial plants. In a good number of these processes, it is acceptable for controlled variables to vary away from the set point as long as the feedback control loop corrects the errors and keeps the controlled variable close to the desired value. But there are some processes in which we want to minimize errors in the controlled variable as much as possible. In these processes, feedback control is not the type of control loop needed. In this segment, we're going to see how a feed-forward control loop can be added to a typical feedback control loop to prevent an unsafe condition from arising. For example, many industrial plants have furnaces that provide heat for various production processes. In the operation of a furnace, there are control loops to maintain the combustion process and to maintain safe furnace pressure. Both of these control loops can be related to airflow through the furnace. Now, let's see how. Exhaust gas from a furnace is vented through a stack and into the atmosphere. Now, various environmental laws require that the amount of ash particles and other substances in furnace exhaust be reduced to a minimum before the gases are vented through the stack. One of the ways to minimize particulate content in the exhaust is by ensuring that enough air flows through the furnace to allow for thorough fuel combustion. If there isn't enough airflow for efficient combustion, then unburnt fuel will be sent out of the stack in the exhaust gases. Airflow in this plant is achieved by the actions of two different fans. One is this FD, or forced draft fan. The FD fan pushes air into the furnace. The other fan is this ID, or induced draft fan. The ID fan pulls exhaust gases out of the furnace. We can see how furnace draft can be controlled using a simplified illustration of the process. In this illustration, there is an FD fan that is pushing air into the furnace and an ID fan pulling exhaust gases out of the furnace and venting it into the stack. The heat generated by fuel combustion in the furnace heats water in a boiler to generate steam. The inner walls of the furnace are made up of water wall tubes. As water flows through the tubes in the furnace, it is heated into steam. The steam collects in a boiler drum, similar to the kind we looked at earlier, and flows out through a pipe at the top of the boiler drum. Now, if there's an increased demand for steam, then there will be an increased demand for water to be converted to steam. This will require additional fuel to heat the water. And if more fuel is needed, then more air is also needed to maintain proper fuel combustion. Here's a greatly simplified illustration of the kind of control loop that can be used to control airflow for fuel combustion. A pressure sensor monitors steam pressure at the point where it leaves the boiler. If the demand for steam increases, steam pressure will drop. A transmitter measures the drop in pressure and converts it to a signal that is sent to a combustion controller. The combustion controller provides an output signal to control both fuel flow and airflow. In this example, we'll only look at the airflow portion of the control loop. The combustion controller provides an output signal to an airflow controller, which produces a signal to increase the speed of both the FD and ID fans, and as a result, increase the flow of air through the furnace. Combined with the increased fuel supply, combustion in the furnace is able to heat the additional supply of water, converting it to steam and restoring steam pressure to the desired level. This control loop is a feedback control loop because when a disturbance causes the steam pressure to change, the control loop provides corrective action to restore steam pressure to the desired value. Airflow is an important variable in this process to maintain combustion and, as a result, steam pressure. Airflow is an important variable from a safety standpoint as well. Total airflow through the furnace, from the FD fan to the ID fan, is controlled to maintain a slightly negative pressure in the furnace. This is accomplished by having the ID fans pull exhaust gases from the furnace a little harder than the FD fan is pushing air into the furnace. The process of combustion in the furnace causes air inside the furnace to heat and expand. If this expansion of air were not controlled, it could eventually cause structural damage in the furnace. This is not likely to occur, and one of the reasons why it's not likely to occur is because the total airflow through this system is controlled to maintain a negative pressure inside the furnace and counteract the expansion of air due to combustion. Now, the feedback control loop adjusts the speed of both the FD and ID fans together. Normally, when it does this, it maintains the balance between the push of air by the FD fan and the pull of exhaust by the ID fan. But in day-to-day operations, the system can get out of balance. That is, mechanical wear on the fans or soot and ash buildup in the furnace or other disturbances can cause the total airflow to change. In order to maintain the proper balance, we can add a feed-forward control loop to the existing feedback loop. But before we look at the feed-forward loop and see how it works, let's review the concept of feed-forward control. With feed-forward control, the value of a disturbance is measured and corrective action is taken in an attempt to correct the disturbance before it can affect or change the controlled variable. In other words, feed-forward control anticipates a change in the controlled variable and takes action before the change occurs. Again, as with a single-element feedback control, a single-element feed-forward control loop has only one primary element, providing only one input signal to the controlling element. Let's go back to the airflow example to see how a feed-forward control loop might work. These devices on the side of the furnace are pressure taps. Pressure inside the furnace is directed through these taps and the tubes to two locations. One of these taps directs a pressure signal to the control room, where the value of the pressure inside the furnace is visually indicated. This signal has no effect on the control of this process, but it does let the control room operators know what the pressure is inside the furnace. The other tap directs a pressure signal to a transmitter. This transmitter functions as both the primary and measuring elements in the control loop for this system. The transmitter senses pressure changes, measures the change, and converts it into an electrical signal, which is then transmitted to a converter. The converter changes the electrical signal into a pneumatic signal before sending it on to a controller. The pressure change is converted to an electrical signal in this example because the controller is at a remote location. An electrical signal can be transmitted over longer distances than a pneumatic signal without significant loss in the strength of the signal. The controller performs its operations of measuring, comparing, and computing, and then sends a correcting signal to the final control element. Here, the final control element is this actuator, which adjusts a hydraulic coupling between the ID fan and motor to vary the speed of the ID fan. Let's go back to our illustration of the process to see how this control loop works. The elements of the control loop are the pressure sensor, the transmitter, the controller, and the actuator. With this completed illustration, we can now see how the feed-forward control loop works to control total airflow for this system. The controlled variable here is total airflow. The manipulated variable is airflow at the ID fan. And the measured variable is pressure inside the furnace. Now remember that one of the variables that is changed to maintain steam pressure is airflow. And if the demand for steam increases, the flow of air, as well as the flow of fuel and water, is increased to maintain steam pressure. Now, when the flow of air at both the FD and ID fans is increased, they should both be increased the same amount. If a problem occurs, for example, airflow at the FD fan is increased more than the airflow at the ID fan, then the pressure inside the furnace will change. In this example, the pressure will change from a negative pressure toward a positive pressure. When this happens, the feed-forward control loop comes into account. The change is sensed by the primary element of the control loop. The signal is transmitted through the control loop to the actuator at the ID fan. The actuator adjusts a hydraulic linkage which increases the speed of the ID fan blades, causing the fan to pull more gases out of the furnace. This corrects the pressure change in the furnace and maintains proper airflow required for safe operation. The reason that this is a feed-forward control loop is because the control loop works to maintain the proper airflow. And as long as the proper airflow is maintained from the FD fan to the ID fan, then the chance of reaching dangerous pressure levels in the furnace is minimized. Now, up to this point, we've looked at a process with a feedback control loop and a process that combined a feedback loop with a feed-forward loop. And so far, we've discussed the loops separately as single-element loops. In the next 3 parts of this program, we're going to look at 3 different multi-element control loops in which the arrangement of the loop determines to a degree what kind of control loop it is. Before continuing, review the material in your text. Be sure you understand the difference between single-element feedback and single-element feed-forward control loops. If you have any questions, ask your instructor. So far, we've seen examples of a process with a single-element feedback control loop and a process with a single-element feed-forward control loop. These processes were fairly simple and required only one sensing element. However, some processes are not as simple and require more than one sensing element. For example, the large tank behind me has 3 temperature sensors to monitor the temperature of gases inside the tank. Now, each of the 3 sensors provides a signal by use of a transmitter to the same controller. That one controller has to measure each of the 3 signals and determine which of the signals, if any, to respond to. Now, this type of control loop is called auctioneering control. We'll look at this process and its control loop in a few minutes. But first, let's find out what auctioneering control is about. In an auctioneering control loop, the controlling element is designed to respond to one signal from 2 or more input signals. The signal that it responds to is usually either the highest or lowest of all the input signals, depending on the process being controlled. Since auctioneering control uses more than one primary element, that makes it a multi-element control loop. Multi-element control means that the control loop has more than one primary element and provides more than one signal to the controlling element. So with auctioneering control, a controller measures 2 or more input signals, but it only responds to one of them. Auctioneering control is a multi-element control loop because the controller receives an input signal from more than one primary element. Let's take a closer look at our example of a process with auctioneering control. Any plant with a furnace and exhaust emissions needs to clean those emissions before they're released into the atmosphere. And the large tank behind me is part of a process that removes impurities from furnace gases before the gases are vented through a stack and into the atmosphere. Now, this tank is called a scrubber. In this process, hot, dirty furnace gases are vented into the top of the scrubber. The gases are mixed with water, which is sprayed in through the top of the scrubber. Many of the particles and impurities in the gas are collected by the water and fall to the bottom of the scrubber, where they're pumped out for further treatment. The cleaned gases are pulled out of the scrubber by an ID, or induced draft fan, through these exhaust ducts, and are vented to a stack, where it's released to the atmosphere. Now, this process is fairly large, and the operations we described, for the most part, happen inside the scrubber. So let's look at an illustration of this process to get a better idea of what's happening inside the tank. Then we'll look at why a control loop is needed for this process and what it looks like. Inside the scrubber, water is forced against a plumb bob and the walls of the scrubber, creating a turbulence. An ID fan creates an induced draft which pulls hot furnace gases into the scrubber. As the gases are pulled through the turbulent water, the water collects particles from the gases and falls to the bottom of the scrubber. The cleaned gases are pulled out through an exhaust duct and are vented to the stack. Now, the inside of this scrubber is rubber lined, and this rubber lining would not be able to withstand the high temperatures of the exhaust gases coming into the scrubber. One reason why the rubber lining isn't damaged is because when the gases mix with water, they cool down. In addition, if the gases do not cool down enough to prevent damage to the lining, an auctioneering control system will shut down the ID fan so that exhaust gases are no longer pulled into the scrubber. Let's take a look at the instruments in the auctioneering control loop for this process. The primary elements for the control loop in this system are temperature probes like this one. There are 3 of these located on the sides of the scrubber. These probes monitor the temperature of the cleaned gases inside the scrubber. Each of the temperature probes is connected to a transmitter, which measures the gas temperature indication from the probe at that point in the scrubber. If you look closer at the indicator on this transmitter, you can see that the temperature indication measured by this transmitter is about 90 degrees Fahrenheit. The set point of the controller is also indicated here for easy comparison. Set point is about 175 degrees. In this process, set point is the temperature at which the control system takes action to prevent damage to the rubber lining. The temperature measurements at each of the transmitters are converted to signals that are sent to a controller. The controller measures each of the signals coming in and compares them to set point. If any one of the 3 signals indicate a temperature above 175 degrees, the controller produces a corrective output signal. The signal from the controller is sent to an actuator, which adjusts a hydraulic coupling disengaging the ID fan from its driving motor, in effect shutting down the scrubber and preventing any more hot furnace exhaust gases from being pulled into the scrubber. Okay, now that we've seen the instruments in the auctioneering control loop for this scrubber, let's use our illustration to see how all of the elements look together. You can see here that the temperature probes are monitoring the temperature of the cleaned gases. The measured variable then is gas temperature in the scrubber. This also happens to be the controlled variable for this process. The manipulated variable is gas flow through the scrubber. So in the operation of this control loop, the temperature probe sense the temperature of the cleaned gas and produce a signal that is measured at the transmitters. The transmitters convert the temperature indications to signals that are sent to the controller. If any one of these input signals indicates a temperature above the set point of 175 degrees, the controller produces a corrective output signal, which is sent to the actuator. The actuator adjusts a hydraulic coupling, disengaging the ID fan from its motor and stopping the flow of gas through the scrubber. Water continues to flow through the scrubber, cooling off the gases that remain inside it. An auctioneering control loop is an appropriate control loop for this process. Now, the scrubber is large enough that the gas temperature inside of it can vary at different points. To ensure that the scrubber is adequately protected from high temperatures, the control loop uses more than one primary element. In addition, the controller is designed to receive all three input signals and act on any one of them. In the next part of this program, we'll look at a control loop for a process which mixes two different variables in specific proportions. But for now, read the material in your text and answer the questions that follow. A common process in many industrial plants is clarifying discharge water before it's returned to a river or a lake. Now, this tank is a settling tank. It holds a mixture of plant wastewater and chemicals. The chemicals collect some of the contaminants in the wastewater, and then the chemicals, along with the contaminants, settle to the bottom of the tank, reducing the concentration of suspended particles. Clarified water is drained off from the top of the tank, where the water is the clearest. Now, in order for this water clarifying process to work, the chemicals have to be added to the wastewater at a specific ratio. If too little chemical is added, the wastewater will not be sufficiently clarified. If too much chemical is added, then chemical is being wasted, and the clarifying process will cost more than is necessary. Now, this kind of process, where two variables are mixed at a specific ratio, and any other process where two or more variables are combined in specific proportions, can be controlled with a ratio control loop. A ratio control loop maintains a predetermined ratio of one variable to another. Let's see what a generic ratio control loop could look like. You can see that this loop has more than one primary or sensing element, and more than one input signal to the controlling element. But unlike auctioneering control, where the controlling element selects one of the signals to respond to, in ratio control, one input signal is used as the reference value for one part of a preset ratio. The other input signal is compared to the reference value and the preset ratio. The ratio controlling element produces an output signal to the final control element that regulates a manipulated variable. Ratio control is frequently applied to processes involving flow mixtures, like the mixture of chemical flow and wastewater flow in this water clarifying process. But ratio control is not limited to flow applications. For example, ratio control can maintain a ratio between two temperature measurements, or two pressures, or two levels. The important thing is that a ratio is maintained between two or more variables. Let's take a closer look at this water clarifying process and its ratio control loop. Many industrial plants use water in a number of processes. As water is used, it picks up contaminants. These contaminants must be removed before the water is reused or returned to a river or lake. One way that this can be done is by using chemicals to remove the suspended particles from the wastewater. A chemical solution is mixed with the plant wastewater in a large mixing tank. Then the mixture of chemicals and wastewater is transferred to a settling tank. Here the chemicals attract pollutants in the water. The resulting mass of chemical and pollutants settles to the bottom of the tank. Clearer water at the top of the tank is drained off into another tank. The water then goes through various other cleaning steps before it's reused or returned to its source. The elements of the control loop for this process aren't too much different from the control elements in some of the control loops that we looked at earlier. The primary element for both the water and the chemical variables is a device like this one that monitors flow. This process has one flow device to monitor wastewater flow and one flow device to monitor the flow of chemical solution. The signal from the wastewater flow sensor goes to a transmitter like this one. The transmitter converts the flow value into a signal that's sent to this controller. The input signal from the transmitter provides the set point for the predetermined ratio that this controller maintains. The signal from the chemical solution flow sensor goes to a transmitter like this one. This transmitter also converts the flow value into a signal that's sent to the same controller. The controller processes this input, compares it to set point, and produces a corrective output signal. The output from the controller is used to vary the speed of a pump like this one. This pump manipulates the flow of chemical solution to the mixing tank. By varying the speed of the pump, chemical flow can be increased or decreased to maintain the proper ratio of chemical to wastewater. Well, now let's look at an illustration of this process and the ratio control loop so we can see all of the elements together. As you can see, there are two flow sensing instruments in this control loop. This one monitors the flow of wastewater that is to be treated. The flow of wastewater to the mixing tank is not controlled and can vary depending on the output from the plant. Since this flow is not manipulated, it can be referred to as the independent flow. This flow sensing instrument monitors the flow of chemical solution to the mixing tank. The flow of chemical solution is varied by changing the speed of the pump to maintain a proper ratio in the mixture of chemical to wastewater. This flow of chemical solution can be referred to as the dependent flow. As the wastewater and chemical solution flow into the mixing tank, both flows are monitored by the flow sensing instruments. The transmitters measure the flow-related information and convert it into signals. These signals are sent to the controller. As long as the flow of wastewater stays constant, the controller will determine that the ratio of chemical flow to wastewater flow is being maintained. That's usually true of most control loops. If the monitored variable doesn't change, then the controller output also doesn't change. Okay, what would happen in our ratio control loop if, for example, the flow of wastewater slowed down, say because of decreased use of water in the plant? As the flow of water slows down, the new flow is measured at the transmitter and converted to a new signal to the controller. This new controller input signal becomes the new set point for the ratio that this controller maintains. The controller then compares the input signal from the chemical flow transmitter to the predetermined ratio and the set point of that ratio. If the ratio of chemical flow input to the new set point doesn't match the predetermined ratio, the controller changes its output signal. The output signal is sent to the pump, adjusting the speed of the pump and reducing the flow of chemical solution so that the ratio of chemical to water is restored to the proper mixture. A ratio control loop is the appropriate control loop for this process. Appropriate because we need to monitor more than one variable, and because we need to maintain a predetermined ratio between the two monitored variables. So far we've looked at two kinds of multi-element control loops, auctioneering and ratio control loops. A third multi-element control loop is a loop called a cascade control loop. We'll look at it and an example of the kind of process it controls in the next part of this program. But for now, read the material in your text and answer the questions that follow. Be sure to check with your instructor if you have any questions. Up to this point, we've seen a variety of processes and the different control loops used to maintain each. And even though the control loops were different, they all had the same objective, and that is to maintain a controlled variable at or near set point, or provide a corrective action when the variable reaches a preset value. The differences were in the requirements of each process. For example, the scrubber process that we looked at earlier required that gas temperature be monitored at several locations, and that any one of the measurements could trigger control action. The control loop that we described for this process was auctioneering. Another process that we looked at, the water treatment process, required that a chemical solution be mixed at a precise ratio to wastewater. The control loop that we described for this process was ratio. Each process that's being controlled has specific requirements that, to an extent, help to determine the kind of control that's used. For example, this process behind me is a heat exchanger process. Now, if we go to a simplified illustration of this process, we can see how it works.
In its basic operation, steam flows through tubes inside the tank, heating water that is circulated through the tank and around the tubes.
Now, one characteristic of this process is that the tank has the capacity to hold a lot of water. Large amounts of water have the capacity to store large amounts of heat. This means that if a disturbance occurs that changes the water temperature at the input, there would be a lag between the time the disturbance occurs and the time it's sensed at the output.
Another characteristic of this process is that the steam tubes resist the transfer of heat from the steam inside the tubes to the water outside the tubes.
This means that if steam flow here increased to correct a change in water temperature, there would be a lag between the time the steam flow changes and the time the water temperature changes. Now, these two process characteristics, capacitance and resistance, cause a significant lag between the time a disturbance occurs and the time it's sensed and corrected. Now, one way to overcome the delay characteristics of this process, if it's necessary to minimize lag, is by using a cascade control loop arrangement. Cascade control is a type of control in which the output of one controller is used as the set point to regulate a second controller. Now, this is different from ratio control, which maintains a predetermined ratio of one variable to another. Again, we can use a simple block diagram to illustrate the concept of a cascade control loop. In cascade control, two or more control loops are arranged so that the output of one controlling element adjusts the set point of another controlling element. This illustration combines the two control loops. This loop can be called the primary control loop. It provides the principal control signal. This loop can be called the secondary control loop. It depends on the signal from the controlling element in the primary control loop for its set point. The controlling element in the secondary control loop provides the output signal to the final control element. If the process here had significant lag characteristics, the secondary control loop divides the lag and reduces the effects of a disturbance in the supply. So theoretically, cascade control helps to minimize process lag and provide a faster control action than would otherwise be possible in a process with significant lag characteristics. Now, let's see how cascade minimizes the lag characteristics of this heat exchanger. Now, first, we'll look at the primary control loop, and then we'll add the secondary control loop to complete the cascade arrangement.
The primary element in the primary control loop for this process monitors the temperature of the water coming out of the heat exchanger.
This temperature indication is measured by a temperature transmitter like this one. The temperature measurement is converted to a signal that is sent to a controller. The controller measures the signal and compares it to set point. The set point for this controller in the primary control loop is set manually. The controller then computes the difference in the value of the signal from set point and produces an output signal. Normally, this output signal would be sent to a final control element, but in the cascade arrangement for this process, the output from the controller in the primary loop is sent to the controller in the secondary loop. Now, we'll see how this is done when we look at the secondary control loop. But for now, let's see how the primary control loop might look if it were the only loop for this process, rather than how it looks as part of a cascade arrangement. What we have so far is a single element control loop. We're monitoring one variable, the temperature of the water coming out of the heat exchanger. Now, this information is used to adjust a steam flow control valve that controls the flow of steam to the exchanger. Let's see what happens if we have a disturbance in the steam flow that causes the flow to increase. An increase in steam flow would cause the water temperature to rise, but because of the lag characteristics of this heat exchanger, the change would be slow. By the time the change is sensed, the water temperature has been away from set point for a fair amount of time. Even though the control loop provides a fast corrective signal to reduce the flow of steam, the change it causes in the water temperature also occurs slowly. If the control loop corrected too much or too little, it would eventually be sensed and a new corrective signal produced. Because of the delay in temperature changes caused by the resistance and capacitance in this process, the water temperature could cycle quite a bit before it returns to set point. Now, if we add a secondary control loop to the primary control loop that we just looked at, we would have a cascade arrangement that could improve the control response to a steam flow disturbance. Let's see what the secondary control loop could look like for this process.
The primary element in the secondary control loop for this process monitors the flow of steam before it enters the tubes in the heat exchanger.
This steam flow is measured by a flow transmitter like this one. The steam flow measurement is converted to a signal that is sent to a controller. The set point of this controller is automatically adjusted by the output of the temperature controller that we saw earlier. We'll see how this works later. If the flow controller determines that the steam flow is too great or too little, it provides a signal to the steam flow control valve.
Now, we said that in the cascade arrangement for this process, the secondary control loop is combined with the primary control loop. But before we see how these two loops look together, let's see how the secondary control loop might look if it were the only loop for this process.
What we have here is another single-element control loop. We're monitoring one variable, the flow of steam going to the heat exchanger. This information is used to adjust the steam flow control valve that controls the flow of steam to the exchanger. Now, let's see what happens if we have a disturbance in the steam flow that causes the flow to increase. An increase in steam flow would be sensed by the flow sensor. This would trigger a signal through the control loop that causes the flow control valve to reduce the flow of steam. The actions of this control loop senses the flow disturbance before it can significantly affect the temperature of the water in the heat exchanger. Now, the secondary control loop that we just looked at was able to correct a disturbance in the steam flow before it could cause a significant change in water temperature. But it may not completely prevent the water temperature from changing. Now, for this reason, we'll combine the primary loop that we saw earlier with the secondary loop to form a cascade control loop. Now, in this cascade arrangement, when there is a disturbance that causes the steam flow to increase, the steam flow sensor triggers a control signal that quickly adjusts the steam flow control valve to reduce the steam flow. Whatever change that does occur in the water temperature is sensed by the water temperature sensor in the primary control loop. The amount of change is measured by the transmitter and converted to a signal to the controller. The controller in the primary loop performs its normal measuring, comparing, computing, and correcting actions. But instead of its output going to a final control element, the signal is sent to the controller in the secondary control loop, where it adjusts the set point of the controller. In a sense, the controller in the primary loop adjusts the controller in the secondary loop according to changes that occur in the water temperature. The secondary loop controller measures and compares the signal representing steam flow to the new set point, computes the difference, and produces a correcting signal that causes the control valve to adjust the flow of steam enough to correct for any errors in the water temperature and to compensate for changes in steam flow. Essentially, by adding the secondary control loop, the system is now monitoring steam flow, determining how any steam flow changes might cause the water temperature to change, and providing control to prevent the water temperature from changing because of steam flow variations. If for some other reason the water temperature does change, the primary control loop provides the information needed to correct the error. The overall effect is to reduce the time it takes to sense an error and correct it. Sometimes both the primary and secondary controllers are contained in the same case. This does not change the effect of the control loop. By now you should have learned that there are many different ways to control the many different processes in today's plants. We have looked at a few of the kinds of control loops that are used, but they are by no means the only loops in use today. Most loops that you will see will most likely be a variation of one of the control loops that we looked at in this program. The important thing to remember is, if you understand the requirements of a process, and if you understand the basic operation of its control loop, then you'll be in a better position to correct problems in the system when they occur.